This fall, we are launching a brand new platform of tools, education, and community to dramatically accelerate the speed of engineering. This platform is specifically built for teams who develop physical goods, such as machines, devices, and consumer products. If you are a mechanical engineer, R&D engineer, process development engineer, mechanical designer, product development engineer, or similar, we think you'll love what we're working on. More info to come soon, so keep your eyes and ears open for the fall launch of the website. In the meantime, send us a note at podcast@teampipeline.us and let us know what features or functionalities you would find most useful in this platform. Hello and welcome to another episode of the Being an Engineer podcast. Today we're speaking with Drew Devitt, who is founder and CTO at New Way Air Bearings, where they manufacture porous media air bearings for high-precision, friction-free motion applications. Now, I actually did an article about their product a little while ago, and it was just such a cool product that I was thrilled when Drew was willing to come on to the show and talk a little bit more in detail about what are porous media air bearings, how are they used, how are they going to benefit you in your engineering applications. So, Drew, thank you so much for being willing to spend some time with me on the show today.
Well, thank you for having me on your podcast, Aaron. I'm glad to be here.
Can you tell us a little bit about your background? You know, how did you get into manufacturing and the porous media air bearing technology?
Well, it's funny you should ask that. And I went to your website and I happened to see how, you describe how you got started and some of the frustrations that you had gone through. So I think we have a similar tale to tell, and maybe I can weave it together here. So when I started, basically graduating from college and all through high school, my parents had a business in the house where they imported a product from Germany called Moglice, which is a moldable slideway material. And my dad was selling it to the U.S. machine tool builders. So the people that build big metal cutting machine tools and grinders and mills and planer mills and things like that. Were users of this Moglice. So he would take me on his business trips. I would get to see these big factories where they were building huge machines, and even just in high school. And then, in college, I did, I guess you'd kind of call them internships, but in the summers, he would send me off to a rebuilder in Milwaukee or in Cleveland or something. And I'd spend 3 or 4 weeks out there, working with them and, learning how to do machine tool rebuilding. And especially, I learned to scrape. I don't know if, it's scraping. It sounds kind of rough, but it's actually a really fine precision art where you take two pieces of usually cast iron and you put them together and you've got this ultra thin layer of blue on one side and red lead on the other side. And then you rub the surfaces together. You push it maybe a half inch at the most, and then you pick it up and you see where the contact was. So you scrape on those surfaces and then stone it off and put it back together again until you get the whole surface to bear properly, right?
Interesting.
So this is the way, they did it the old days, right? So the Moglice was a moldable material. So if you had one surface that was perfect, you could mold the other surface and then you'd have a perfect fit. You wouldn't have to scrape them to fit, but you would still have to scrape one surface to get it to be right. You needed one good surface. So I had to learn how to scrape, and then I learned to apply the Moglice material, and I wound up going around training rebuilders how to apply this material. And then when I got out of college, I was, trying to get the business big enough to move out of the house, right? But I had a paradigm problem, right? So the machine tool builders, not only, the 80s, it was a rough was a rough decade for them. A lot of them were going out of business. And for me, it was rough. Not only were my customers going out of business, but a lot of them were changing over to linear guide systems, trackway systems where you've got a guideway that's hardened steel, and it's got ball races or cross roller races, and you bolt it down, and it's got a truck, and you bolt something to it, right? Well, that was like the death knell for scraping, right? And plain ways. So, I could see the market for that was tanking, and I better come up with another program if I was going to retire in this business. So I developed hydrostatic bearings. I thought hydrostatics were the way to go first because I could still mold them with the Mowgli's. I could mold the pockets in. And so that wasn't very successful, though. And, at this point, I was probably already drinking, right? And I'm at the bar with my dad and one of his friends from Oak Ridge National Laboratory. And he draws on a napkin like engineers do, and so he draws, a couple bearing housings, basically, that he wanted me to make. And then he sent me some of the graphite, to make the graphite wafer to go in there. So basically he, told me how to make these bearings at the bar, gave me a napkin, slapped me on the back, said, make me these bearings, right? So I did. And it was interesting, like, especially milling the graphite, right? So in high school, I had also gotten a job at a local machine shop, because I was already kind of into machines and that kind of. So one of my friends had a father that had a machine shop. So I started working at the machine shop. This was like probably 1978, so it's a long time before, right? But the machine shop was interesting because the dad sort of took me under his wing, and I was working with him in the back, and he was the owner of the business, right? So he was an interesting mentor for me. I learned a lot. And I think he was really just trying to spy on his own kids. He wanted me to tell him what was going on. But anyhow, I had a nice start in the machine shop. So this was actually years before I had made these bearings for my dad's friend, and machining the graphite without a dust collector was an experience. I couldn't even see the part.
Wow.
In the handles.
Yeah, bad.
But anyhow, they worked out for him. And then years later, he ordered a couple more, and I found some other people to buy some. But I'm still, 95% in the Mowgli's business. So then he gets a job as chief engineer at Starrett. So Starrett's a metrology company. They make a lot of micrometers. Well, they decided they wanted to go into the coordinate measuring machine business, and that's right near Oak Ridge and where they were down in North Carolina. So he designed 7 or 8 brand new coordinate measuring machines, and they all used my air bearings. And so, that's where I really had my first OEM for the air bearing business.
And to be clear, the graphite that you were talking about, that is the air bearing, right?
Right. So the graphite it's the restrictive element in the air bearing. So normally we still use metal in most bearings. You can make a bearing completely out of graphite, but we use metal because it gives you a higher modulus. So you can carry more weight.
So let's talk about the physics of the air bearing a little bit. I mean, when people hear air bearings, before I knew about porous media air bearings, I would think of an upside down air hockey table, right? Like a metal puck that blows air out the bottom and creates just a little bit of lift so that whatever your payload is on top feels much less heavy and you can move it around a work surface. But the porous media air bearings, they work similar but different than I'll call it the upside down air hockey table. Tell us a little bit about the physics behind how porous media air bearings work.
So all air bearings basically have some sort of a restrictive element, right? So if you didn't have a tube going to every air bearing, the one on the bottom that doesn't have any clearance, like all the air would just rush out of that one, right? So all the air bearings, if they're plumbed to a common source, need to have a first restrictive element so that, if one becomes completely unloaded, all the air just doesn't come out. So orifices are one way to do that, right? But porous media, right, whether it be a ceramic or a graphite or a carbon or a bronze or aluminum or granite is actually porous. Neodymium is porous, right? So we've made air bearings out of all these things. The key is that it's a restrictive element. And then the second restriction in an air bearing is the gap itself, right? So the air is trying to get out of the gap, right? But the gap is so small that it can't get out right away. And there's constantly new air coming in, even as it gets out the edge. And so that's what actually carries your load or your weight. And so with air bearings, generally, if you put in, say, 100 PSI, you're going to get maybe 50 PSI of unit loading underneath the bearing. Put in 60 PSI, you'd probably get around 30. What's interesting, though, is if you put in 1,000 PSI, you get closer to like 900 PSI of unit loading. So you only need that, that first delta of a few bars worth of pressure.
Yeah. Okay. And with orifice air bearings, typically there's just one orifice, or maybe there are 2 or 3 or 4, but they're a very small few. Whereas with porous media, because of the nature of the material that you're using, there are, I think, millions of these microscopic orifices, for lack of
right, millions,
right?
There's millions of these little submicron orifices, and you'd think, well, wow, that would plug up, right? But what's interesting is that's the reliability problem that orifice bearings have, right? Because here you've got this orifice, let's say it's a 6,000 diameter hole, or maybe it's a big one, it's like 10,000, right? Well, it doesn't take much of a particle to plug that up, right? And it's really hard to keep particles out of a system. Something's going to slough off the inside of a tube, or a little Teflon tape is going to be in there, or somehow, that orifice, at some time in its life, it's going to get plugged, right? But with a porous bearing, you could go ahead and pour sand into the bearing, or stuff Teflon tape in there. You can just about any kind of contamination you can put in there. You can fill up the whole plenum inside of the bearing with stuff that would plug an orifice bearing, and it won't have any effect on the porous bearing because it's got less restriction than the porous media, right? So it's not even going to slow down the flow of air appreciably.
Yeah. Very cool. Now, what are some of the, let's call them environmental constraints within which one needs to work when using porous media air bearings? For example, the surface flatness of the bearing surface, or the surface underneath the bearing on which it's riding, things like that.
Right. Well, for sure, that is an important element. And there are different types of air bearings. There are air bearings that are used by riggers. I refer to them as skirted bearings, right? So they'll allow you to move really heavy machines around on floors that are pretty rough. But, they've got a skirt to keep the air pressure underneath, right? We don't have any skirt or any contact at all. And so we let the air come right out the edge, and we depend on a very small gap. So a flow through a gap for a given pressure is a cubed function of the gap. So as the gap keeps getting smaller and smaller, the restriction goes up in a big way. And so it's very interesting, and maybe we'll talk about this a little later, but air bearings can have a big range of stiffness because of the air gap. You can go from having almost no stiffness to having nearly infinite stiffness in 1,000th of an inch.
Yeah, let's talk about stiffness. What does that mean specifically within the context of these air bearings?
Well, stiffness is it can become a very complicated thing. So I think I like to try to simplify it, right? So if you think about damping, it's basically a combination of motion and force, right? So how much motion is there and how much force is there, does it take to have that, right? So that would be stiffness, right? Like how, if you put a force on there, how much does it actually move, right? So if you're thinking about damping, you can't have any damping if there's zero motion, right? So if you've got infinite stiffness, you've got zero damping. But if there's zero force, right? If you push on something and there's nothing, then you've got zero damping, right? Because you've got zero stiffness again, right? So you have these two opposite spectrums with respect to where you've got zero damping, right? And for a given frequency, there's going to be some point, so if you increase your stiffness and increase, your damping's going to go up and up and up to some point, and then if you go make it any stiffer, then the damping's going to start to go down. And so, that's a really simple way of thinking about damping stiffness.
And damping these, forgive me for interrupting, these air bearings are often used in very high precision applications. You mentioned CMM, right? Obviously, metrology, it needs to be really super accurate. And so if you have, because the bearings are riding on a film of air, if it was to be not very stiff, in other words, it could fluctuate up and down on that film of air, then your measurements could be off. So it's really important that you have this stiffness, and that's why that's the phenomena that we're talking about right now. And the film of air on which these bearings ride are typically somewhere around like 5 microns, something like that. Is that right?
That's correct. That would be sort of a target where you're going to have really good stiffness and good damping too.
Yeah. Okay. And because you have good stiffness, it stays at around 5 micron, maybe at plus or minus 1 micron or something like that. But it's really stiff so that your measurements, whatever your application is, doesn't inherit the what's the word I'm looking for? Variability that would be inherent with low stiffness.
Right. And, there's the idea of dynamic stiffness, which, for instance, there's all kinds of things on a CMM that are moving around, right? And all sorts of sources of vibration. And sometimes, especially when you've got like a long arm and it's sticking way out, the last thing you want to do is try to set up some sort of a vibration mode, right? So you want your air bearings to be consistent with thud, not ring.
Yeah. Let's talk a little bit about the carbon nature of these porous media bearings. When I first learned about the carbon, I thought to myself, oh, well, shoot, this won't work for a lot of our applications because a lot of our customers are medical device customers, and the equipment that we develop at Pipeline goes into a clean room, and, well, carbon flakes off so easily, and so it can't be used in a clean room. So thus, this technology wouldn't be a good fit for us. But as I learned, that is not the case. Can you talk a little bit more about why the carbon material actually does work and is used quite often in clean room type settings?
Right. So, the big key there is that the air bearings aren't touching, right? So they're not actually, they're not wearing. And so the particles aren't coming off like they would be coming off of a rolling element bearing or a plain sliding bushing or something like that. So, the big key is just non-contact is a good way to, avoid particulation. And so in a lot of those cases, people leave the machines running all the time, like, lithography machines, right? Those machines run 24 hours a day, 365 days a year, that never get turned off. And so the bearings don't touch and they don't make particles. And we managed to get into some pretty sophisticated machine tools or lithography type machines where you wouldn't expect to be able to put a piece of graphite like that. But,
yeah.
So, yeah.
How about the different types of bearings that New Way Air Bearings offers? The ones that we used were round, flat air bearings. but you offer quite a few different varieties. Can you talk a little bit about the different options available to engineers who might want to incorporate these into their application?
Sure. Well, the puck bearings, both rectangular and round, are probably the most standard broad brush product that we're selling. You can size them based just off of the size charts and as far as the load, but they're a little different. You're going to be building a machine along the lines of a metrologist or semiconductor stage builder or something like that. It's not bolting down the linear guideways. But we're glad to help you with that, and it's really a lot simpler than you might think. Contrary maybe to your experience, Aaron, but I'm glad it all worked out.
It all worked out in the end.
So those bearings mount, basically on ball studs. So you just adjust them until you've got your stage lined up right where you want it to be. And then your preload ones, there's a couple different ways you can preload them. You can just turn the pressure down to like 30 PSI. If let's say you're running at 60 PSI, turn the pressure down to 30 and just keep tightening the preload bearing until it just starts to drag, and then turn your pressure back up to 60, and that would be a good place to be.
And the preload that you're talking about, this is what's referred to as a VPL, or vacuum preload bearings. And this is another type of porous media air bearings that includes a vacuum, which seems a little counterintuitive. At least it did to me at first. It seems like the vacuum would counteract the effect of the pressure that you're using to create the air film on which the bearing floats. Can you talk just for a minute again about why is it necessary to have this vacuum? What's the benefit of doing that? Doesn't it just counteract the effect of the pressure that you're putting in?
So some precision engineers and stage builders, like the idea of not having stacked stages. They want to basically use one plane as a reference. And so if you can build a bearing system that can do both X and Y on one surface and not have to be stacked and deal with the problems of a stacked stage, you can really chase a nanometer, whereas you couldn't do it when you were on these stacked stages before. So the ability to float on a flat surface is great, but unless you have a lot of mass, you might not have much stiffness and damping in your air film. So now you've got, this perfectly flat surface that you're going around on, but you're kind of on a water bed. And so if you don't want to add mass to the system, and you can't really do magnetic preload because you're on granite, you can run vacuum to it. And counterintuitively, we use the high pressure of the air bearing gap to seal the atmosphere from getting to the vacuum. Because the air bearings have such a small flow and the gap is so small, you're able to keep a vacuum in there without much draw, because there's not much air going into the vacuum chamber. And then the pressure differential basically, as the atmosphere pushes the bearing down onto the granite and gives it more stiffness and damping. And now you can drive your stage around, on your perfect plane and have really good vibration resistance.
Yeah.
Good stiffness.
So the vacuum preload effectively just increases the stiffness and thus the accuracy of your bearing, right?
Right. And so in those cases, you're actually holding the stage down too, right? The vacuum. So you don't want to hold
without
just
having
the bearing.
to load it.
You want to actually hold the stage down too. So you don't want to just set it on top of the bearing like you do with a ball stud. So that's when you might use a flexure like you had your experience with, that can, pivot in more than one direction and allow the bearing to accommodate, machining errors and become flat with the guideway.
Yeah. Yeah. Well, let me take a very short break here, share with the listeners that teampipeline.us is where you can learn more about how we help medical device and other product engineering or manufacturing teams develop turnkey equipment, custom fixtures, and automated machines to characterize, inspect, assemble, manufacture, and perform verification testing on your devices. Today, we have the pleasure of speaking with Drew Devitt, founder and CTO at New Way Air Bearings. So, Drew, you mentioned a few iterations that I had to go through, my team went through when we were getting up to speed with the air bearings. And let me just say that it was it was all spelled out in the very thorough and comprehensive design guide that you folks put together. And as any good engineer would, we discarded the instructions altogether and just tried to do it ourselves because we thought, hey, we're engineers. How hard could this be, right? And turns out it's not hard, but there are some critical pieces of information that would have been very obvious had we just read the design guide in the first place. And one of the things that you mentioned just a minute ago was the use of these flexure mounts. And these flexure mounts, there are a few different styles, but maybe I can talk about this for just a minute because we got to evaluate both. I assumed that these flexure mounts would be pivoting on some type of spherical bearing, some type of ball that would allow it to pivot in all directions. And there is a style like that. But what I didn't realize was there's also another style that basically relies on the elastic deformation of a small wall of material in the bearing itself to allow a very small amount of flexure. And if you push those too far, they will break, as I learned. But if you have a pretty flat surface to start with, you really don't need a whole lot of flexion. And so to paint the picture of what we were doing, we had 3 of these puck air bearings that were mounted to what we thought was a flat plate. But when you get to kind of a microscopic level, of course, the plate, it was not precision ground. And so it wasn't really flat. And so when you look really, really, really close, it may have looked like a Pringles potato chip, right? Kind of wavy. Instead of mounting the bearings directly to that plate, which is what we did first and did not work, one of your wonderful application engineers suggested that we use these flexure mounts. And as soon as we did that, everything worked great because the mounts allow those pucks to pivot just a little bit so that all 3 are in perfect planarity on top of the flat, in our case, it was a granite surface that we were using. So for all the listeners out there who want to try using these air bearings, just know that you need to use a really flat surface to start with, like a granite block or maybe glass or ceramic or some kind of precision ground metal. But you also need to make sure that if you're using multiple flat air bearings, they have to be very, very planar with each other. And the way to do that is to use these flexure mounts. And as soon as you use the flexure mounts, everything works very, very well.
So, Aaron, I was also talking about some of the other bearings that we make and how they mount. Can I just try to do a little bit on it? Because it bears on what we're talking about here, right? So there's the flexure mounts, but we also mount on O-rings. So like our bushings, you'll see just have got O-rings around them. And so you can push them into a pillow block, kind of like you would conventional plain bushings. And the compression of the O-rings allows for the bearings to kind of find their home, inside of the pillow block. So they might not be perfect, but a little bit of compliance from the O-rings, as long as that doesn't really hurt you in your stiffness budget, having an O-ring in there. With most people don't have a problem with that. In fact, bushing stages, when you really look at it, it's usually the shaft that has got lower stiffness than even the O-ring does. But at any rate, another way of doing it would be our bonded bearings. So if you have space constraints, you don't have a lot of room to be able to put in a ball stud, or you can do what we had to. In fact, my first patent, the vacuum replication process. The idea was that you take an air bearing and it's flat, and you put vacuum to it instead of pressure. And so you put all the air bearings that you want, it might be 10 or 12 air bearings. They all get vacuumed to the guideway, which is perfect. and then you put your stage on top of it and you line it up, and then you inject the Mowgli's, of course, right? The replication material I was talking about. And so then that cures, and now you basically have no clearance in the system. And so now you put the pressure to it, and it floats back and forth perfectly because the bearings are fit.
Interesting. So does that infer that you need to have a precision ground plate on which you're adhering those bearings?
No, that's one of the big advantages. You really don't have to, whatever you're bonding it to doesn't have to be perfect, right? You just wanted the surface to be rough so the glue sticks to it well.
Interesting.
The Mowgli's, right? So that allows you to get all 12 of those. You'd have to do a very expensive match grinding process to try to get anything that is as close as you can do with the sucking the bearing on there and squirting the Mowgli's. And
interesting. Is that an application that engineers can do themselves with some sort of kit they purchase from you, or is that something that your team would do internally and then send out to a customer?
It is that you can do that. In fact, the other customers too, like for instance, with the bushings, they're designed so that, if you build the stage up and you don't want to have the compliance of the O-ring, we've got holes set up in the pillow block. So when it's floating just the way you like it on the O-rings, you can inject the Mowgli's in, and it goes between the O-rings and comes back out the other side. So you get basically locking the bushing in place once it found the home that it already wanted to live in, the air pressure on. So you can basically seat air bearings in position using an epoxy or a replication material. You want to be careful that you use an epoxy that has got a low shrinkage. A lot of epoxy, especially if they're quick curing, won't work. There'll be too much shrinkage in it for you.
That's really good to know. I don't think I realized that because the flexure mounts that we're talking about, they're, an inch or two tall, and so they can eat up some height if you're trying to work in a low profile application. So it's really good to know that there is another option for mounting these that doesn't increase your overall the height of your application, whatever that might be. Okay.
Right. So you can get your bearing, it can all be in less than half an inch of thickness there.
Wonderful. All right. New Way describes their bearings as creating frictionless motion. And can you give listeners a sense of just how true that is by talking about what is the coefficient of friction in these porous media air bearings?
Right. So coefficient of friction is basically how hard you have to push something to get it to move, and so plain sliding bearings, the coefficient of friction is generally about 0.1. So if it weighed 100 pounds, you got to push on like 10 pounds to get it to slide, right?
And plain sliding bearings, are you referring to like a ball bearing carriage that would slide on a rail, something like that?
No, plain sliding bearings would be like a bronze bearing or a brass bearing or a Mowgli's bearing or a PFET, like a Teflon type bearing, right?
Basically some bearing material on
material, just plain materials. Usually that's a lubricated surface too, right? So that's the kind of friction where you're going to have, about 0.1, right?
Yeah, which generally feels pretty good, right? I mean, 0.1 coefficient of friction, that's pretty smooth.
Right. That would be for a plain bearing. So I'm talking about bearings here, and so that would be about the coefficient of friction of a plain bearing. Then you go to a rolling bearing, right? And that's about 2 orders of magnitude, right? So we're talking about like 100 times less friction than that. So you're now 0.001, right, for the friction that you would see in a rolling bearing, and that's, at zero velocity basically. So that friction will go up as your speeds go up. And then when you get to fluid film bearings, where you're floating on a film of air or water, right? You go another 2 orders of magnitude basically, or another 100 times, right? So now you've got 4 zeros, after the dot and before the 1, right? So
incredible.
It's not it's not zero friction. You're right, but if you think about some of the ESG applications that air bearings could go into, right? Like look at a converting line, right, or a newspaper printing line, right, where you might have 100 rollers in this thing. They're all different sizes, right? They've each got a motor and an encoder on them, right? And you're trying to get them all going at the same surface feet, right? And the motors really are not putting work into the film, right, or into the paper, right? Almost all of the work is just in keeping the rollers turning, right?
Yeah, right.
And you think about the energy that all the motors are using, and if they were on air bearings, right? So now the motor really is only working to get the roller up to speed, right? And at this point, it would spin there like all day at that speed, right? So now it's not having to put work or energy into it, right? So you could save, 95% of the energy of a big converting line or printing line, with these bearings, right? Yeah. And then there's other applications too, where so much of the power is being used in the process, right? Like say a 35 megawatt, or let's say 50, because it'll make it a 50 megawatt compressor, right? It's pumping natural gas, right? Compressing natural gas. So, it's probably got 2 or 3% loss in shear, right? But that means like 95% or 97% of the energy is going into compressing the gas, right? So it's very efficient that way, right? But then you think, okay, well, a 50 megawatt machine, 3% of that, right? Like that's like a megawatt and a half, right? Or I mean, it's a lot, right? It's a lot of power, right? And you think, okay, well, if we can save that power, I mean, that's still a huge savings, right? Because the heat, they were using probably 850 horsepower just to cool the oil, right?
Yeah,
in a machine like that, right? And so now you don't have to do that anymore. So there's big savings that are available because of the frictionless nature. And so for us, we think that we can really take the friction out of the world, and hopefully lubricate things and make things a lot more sustainable with our technology.
Well, speaking of a compressor, let's say that I am an engineer looking into air bearing technology for my application, and I think to myself, wow, millions of submicron orifices through which all this air needs to flow. I'm going to need to generate a lot of compressed air to use these things. I don't know if I have enough compressed air. Are we going to have to put in a new system of compressed air, additional shop air? What kind of flow rates are typically required, and are they really high, or are they pretty manageable? Something that you could take care of even with like Home Depot air compressor.
Right. Well, it depends how many you're running, but it's surprising how low the airflow is. So, we can go in and do demos with pretty big equipment, using keyboard cleaner, as our compressed air supply, So
that's amazing.
Sometimes we do it at the trade show, and we might use, in a full day, if we go through 2 keyboard cleaners, it's a lot, right? So for a pretty big demo that's there, and people are just, oh my God, I can't believe it. And, even when you've got a bearing that's plugged into 100 PSI of air pressure, if you put it up to your cheek, you can still barely feel the air coming out. It's not like, there's any kind of jets and because of the porosity, that's another thing, an orifice, we would definitely feel a stream of air shooting out, right? But porous bearing can have the same flow as an orifice bearing, and you don't even notice the air coming out of it unless you put it underwater to look at the bubbles or something.
Yeah.
And the gaps are so small, right? And because of that cube function that I mentioned, those small gaps are really effective at keeping the flows low.
We had a couple of different round flat bearings, but the smaller of the 2 sets that we used were 25 millimeter diameter, and we had 3 of those supporting our payload. and we had about 50 pounds of mass that was being moved around, and it was, effortless to move 50 pounds with three basically 1-inch diameter air bearings on the bottom. So these were I think these were actually the smallest size of the round flat air bearings, and they get much larger than that. What kind of masses can be supported? Up to how many pounds of mass can be supported with these?
Well, it's really just an issue of pressure times area. So, we're developing air bearings where we can put over 1,000 PSI of pressure to them. So, that gives us an opportunity to get 900, 850 PSI of unit loading, which is about as high as you can get for the tilting pad oil bearings that, are on most steam turbines and, big gas turbines and compressors like we were talking about. Those are all tilting pad oil bearings. So they're fluid film bearings, but they're hydrodynamic. So it's because of the motion of the shaft inside of the bearings that pulls the oil in there. And so they can get up to about 900 PSI unit loading with those bearings. And so we're rivaling them with our gas bearings.
Yeah. And especially, I guess regardless of what type of bearing you're using, you can always add more bearings to increase that surface area, which effectively increases the payload, right?
Well, you have to be careful there, right? Because as a precision engineer, you don't want to over constrain something, right? So like, for instance, the stage that you built had 3 bearings because it was kinematic, right? So it's like a 3-legged bar stool, right? So, if you put it down, it doesn't matter if the surface isn't flat, right. It'll always create some sort of a plane because 3 points define a plane.
Yeah.
You try to put a 4th bearing in there and you can have trouble with over constraint, or basically tipping back and forth on 2 of them, or so.
Right.
But
okay.
You're right. Sometimes we use 5 bearings, right? And so there's other ways. Sometimes they might be spring loaded. So imagine you've got a ball, right? You've got 5 bearings, and you put all 5 bearings, but between the bearing and the ball, you've got a Belleville washer. And they all have the same spring rate.
Yeah.
And so now, you can carry load on all those bearings, but it's not going to have maybe the same stiffness that you're looking for. But
got it.
In a lot of cases, you don't want it to be as stiff as the hard mounted bearings are anyhow.
Yeah. So there's really a lot of versatility at the end of the day here.
Right. There's a lot of different ways to mount the bearings for sure.
Yeah. How about the lifespan of these air bearings? How long can they last? It probably depends to some extent on the environment, how they're being run, but is there kind of a general rule of thumb to follow?
The problem with being an air bearing manufacturer is there's really not a good replacement parts business. Most bearing manufacturers get a replacement part business. We really don't have much of that. Some of the older CMMs, when they come down, they'll replace the air bearings, but just because they're rebuilding them, so they put new ones in, but there's really nothing wrong with them. You could tune them up a little and they would probably keep working for another 20 years. It's when you go and you look at some of these big CMMs at big manufacturers, right? Let's say they're a turbine builder, right? And they've got a big coordinate measuring machine right there, and I can go over there and show them, well, look at this filter and dryer, right? I don't think that's been changed in a decade, right? And in fact, it looks like it probably came with the machine new, right? Like, and that machine's still running, right? And they're not having any problems, and they don't see it as a maintenance issue, even to change the filters for the air. Yeah. So we don't have a lot of problems, from air contamination into the air bearings, and we don't have a lot of problems from the bearings wearing out because they're not touching, and even they're really good in some applications that you might find, like for instance in powder applications. Graphite's a a material that's approved for FDA applications. And when you have an air bearing that doesn't require any oil, that's a big advantage in FDA applications. And then when you've got a bearing that's really a seal too, right? Because it's got high pressure coming out of it all around the edge. So, if it has to run through a powder environment, it just kind of blows the powder out of its way and leaves this beautifully clear track there.
Yeah. Yeah. The fact that there's no contact is really a big deal when it comes to longevity of these devices.
Right. And, that there's no oil, because, oil's really sort of the sticky wicket that that collects all the stuff that wears the bearing out. It provides the lubrication, but, it's basically the lapping slurry that's the ultimate death of the bearing.
Yeah. Yeah. Pulls in all the particulate from around it and keeps it in there. Yeah. All right. Well, Drew, this has been super informative. I love the technology. It was honestly kind of like magic once we got it up and running. I mean, you just nudge it with your finger. This thing floats effortlessly across the surface. Really cool stuff. Anything else that we haven't touched on that you think engineers should know when considering porous media air bearings for their applications?
Well, I think, one of our least exploited technologies are the radial air bearings. So basically, we'll take our rectangular sized standard line, and instead of just putting a flat surface on that bearing, we'll put a radius on it. And so we'll cut that radius by the length or by the width. We'll cut it concave or convex, right? So you can run films over it without touching it, right? You can, obviously support relatively large rotors, right? Easily, because now you don't have to have a big slewing ring bearing, right? And they match really well with linear motors that are curved. So there's a lot of linear motors coming out nowadays that aren't linear. They're meant actually for perimeter driving, rotating equipment, like a baggage scanner or a CT scanner, right? Where you've got a big hole in the middle. You want to be able to support the rotor at the perimeter. So that, I think, is a huge potential, because when engineers start thinking about, wow, I don't have to have a shaft in the middle anymore, it's just so freeing. And it's so convenient to build up big rotary systems on just 3 bearings, radial bearings, and 6 axial bearings, basically, that are squeezing at 3 points, right? So you can constrain your axis of rotation and your point axially, just with 9 bearings, and that are a really small percentage of the total circumference.
Yeah, amazing. So many applications that this could be used in.
Right. And of course, I mentioned turbo equipment. So we're very interested in high-speed rotating equipment. So the air bearings are very good for that. And then we've got a lot of IP and experience in floating flat panel glass. So basically making display glass by using the vacuum and the pressure technologies that we were talking about. And then that has led us to the flexible electronics industry. So you're going to see a lot more of printing electronics on flexible substrates for like solar panels that go on windows, and wallpaper that is the LED light, like the wall is actually the light. Flexible electronics that'll be on people's clothing, and that's starting to become pretty big too. So as a fashion statement. So there's lots and lots of potential applications for flexible electronics, not just in displays, but the ability to have an air turn is what we call it. So it's basically an inside-out air bushing, so that the substrate can float over this roller that doesn't turn, right? Because it doesn't touch, so it doesn't have to turn. And so because the substrate doesn't touch, it means you can build up functional electronics like photospacers and things on it and not ruin them by running it against a roller, right? So now you can touch both sides of the film, and then if you squeeze the film between two air bearings, now you've got it in a really safe place. If you were to just, like they do with the flat panel glass, they squirt cleaning solution on it and they scrub it and then they blow air on it. But if you try to do that with a flexible substrate, it's going to flap like a flag in the wind. But if you put it between two air bearings, then you can have high pressure grooves and low pressure grooves and get these really high speed air films that have a good convective film coefficient to change the temperature of the film, to clean the film, to dry the film. Then we can even pass the film through really deep molecular vacuum for coatings. So because a lot of the electronics industry requires vacuum deposition processes. So we can even get the film in and out of vacuum chambers using the air bearing seal, just like that vacuum preloaded bearing that you saw. How we were controlling the vacuum with the air bearing? So we can do that even down to molecular flow.
Fascinating.
So anyhow, thanks for letting me get some of that out.
Absolutely. Yeah. Yeah. Well, Drew, how can people learn more about New Way and the products that you offer?
Well, the New Way website is probably the best place to go. If you type in air bearings on your browser, probably New Way is going to be the first natural search. So we're probably not buying the first spot, but when you go down, we'll be the first natural search. So the website's a great place to go. I have a lot of videos up on YouTube. You can find that for drew.devitt at youtube.com. And my email would be ddevitt@newwayairbearings.com.
Great. Well, we'll list all of those in the show notes as well, so it's easy for all of you to click through and find all this information. Drew, thank you again so much. What a insightful and informative conversation this has been. Thank you for spending some time and sharing this technology with all the engineers listening.
Well, thanks for your great questions and the opportunity to answer them.
I'm Aaron Monker, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing turnkey equipment, custom fixtures, and automated machines, and with product design, visit us at teampipeline.us. Thanks for listening.